Happy Friday. How are we feeling? I asked that already. All right. On Wednesday, we started talking about the differences between elastic and inelastic collisions and began working an elastic question that we're going to finish up today. Any questions about anything at all before we get started? All right. Let me know anything that does cross your minds. Now, last time, just to briefly review, looking at different types of collisions, the two main types are inelastic, where non-elastic objects are colliding. They share, the rule of conservation of momentum does apply to those types of collisions, but you tend to lose a lot of the energy because the objects involved aren't elastic. They can't store it temporarily as EPE, and so kinetic energy is just not conserved in those types of collisions. As a result, inelastic collisions tend to be very boring, literally very low energy. The objects tend to stick together and don't ricochet away from each other. This is opposed by elastic collisions, where elastic objects collide. And in those situations, kinetic energy can be conserved from start to finish because the objects, being elastic, are able to store their kinetic energy and then release it again rather than just losing it and wasting it on impact. So these types of collisions tend to be very exciting, high speed, things bounce away from each other because they keep their kinetic energy and therefore they're able to move faster. Because of the differences between the two, cars are designed to crash inelastically because it's safer and lower speed, and so that you don't bounce away and launch into oncoming traffic or into a building. And to kind of demonstrate why elastic car crashes would be a terrible idea, we started working a car crash question as if it were elastic, just to see how bad it could get. The two cars involved are one self-driving sports car and one self-driving truck driving towards each other at very high speeds. We determined via conservation of momentum that there is a lot of momentum involved in this system, even though it does point in the direction the truck is moving, because momentum is a vector, so it does care about that. And this is very bad news for the sports car, because if the system's momentum points this way, the car is working against that, and we're going to prove today how bad that is going to be for the car. Now, the problem with a lot of elastic collisions is you cannot guarantee that the vehicles or the colliding objects are going to stick together. Therefore, you cannot guarantee that they will have the same final velocity. So the problem that we ran into is that if we treat the two VFs as separate and distinct, well, then they're not the same variable, and now we have two unknowns. In a lot of inelastic collisions, the objects do stick together, in which case it would be the same VF like we did with the log and the arrow, and then this wouldn't be a problem. But here, since they're likely bouncing away from each other at different speeds, in different directions even, we can't assume that, and we need a second equation with the same two unknowns. Now, the purpose of this slide is to point out that depending on the type of collision, you do automatically have other equations that you can consult, because if the collision's elastic, you can conserve kinetic energy like we conserve momentum. And so all of this work was conservation of kinetic energy to determine a second equation with the same two unknowns in it. And this works because momentum and kinetic energy have the same two unknowns in them, mass and velocity. So conservation of kinetic energy, looking at the total KE before versus after, can give you a similar formula with the same two unknown final velocities in it. And this is a second equation with the same two unknowns in it that we can use to plug into the first one and figure them both out. My problem with this method is that the equation we determined has squares in it. And therefore, if we try to solve for either of those things, we end up taking the square root of an equation with our other squared buried inside of it. So if we did bring this over to try to solve for one of the two equations, we are gonna have to parse through that entire squared and square root situation, and it's just kind of a headache. It works, it just takes time. It does work, but for simplicity's sake, I prefer using option 3. This is a third equation that some very smart people derived from this one. So this is basically conservation of kinetic energy 2, the sequel. This equation is designed to tell you the difference between the two velocities of two colliding objects as long as the equation is elastic, only between two objects, and only one dimensionally, which basically all of the collisions we look at are two object, one dimension, but it is an important disclaimer. This also only works again for elastic collisions. If you're doing an inelastic one like the arrow and the log, you cannot jump straight to this, unfortunately. It just won't work. But 1D, 2 object, elastic, this is great because you don't even have to factor mass in, it just has fewer terms in it, and there's no squares. Meaning we could use this as our second equation with the same two unknowns in it. You just have to pick which object is 1 and which object is 2, and then be very consistent with that, noting that on the right side of the equal sign, the positions of the two objects reverse. It's V1 initial minus V2 initial equals V2 final minus V1 final. That is on purpose, it's not a typo. You have to write it that way or it breaks. But another equation with the same two unknowns in it, what I've got over here is I just decided car is 1, truck is 2. So using that equation as our second equation, we would get 45 minus negative 45, that's V1, V initial car minus V initial truck. V initial truck is just itself a negative number since they point in opposite directions. So this left side is actually going to add up to 90 rather than canceling out. Then on the opposite side, since it reverses, it's VF truck minus VF car. Since on the left, where it's reversed, it was car minus truck, here it's truck minus car. Again, that change is on purpose. The formula is written that way on purpose. It's on your formula sheet labeled as such. Make sure to not transpose them by accident. But this equation has the same two unknowns. We have truck, we have car. There's no squared. We can pretty quickly just solve it for one of them and bring it over into our other one. So if you're working in elastic collision, you actually have 3 equations, 2 unknowns, and you just have to pick 2 of them. My preferences are conservation of momentum and this third one, just for simplicity's sake. Kinetic energy is great and all, but that squared kind of, it can ruin your day. Bless you. I assume that was a sneeze. So you can pick any 2 out of the 3 if you don't know both final speeds. I'm just choosing 1 and 3 just for simplicity's sake. So questions before we start plugging things into other things and try to figure out the final speeds. All right. So equation 3, the left side is going to simplify down to just positive 90, since again it's 45 minus negative 45. And we just have to solve it for one of the 2 unknowns. I'm choosing to take the negative 1 and send it over just to get rid of the negative sign, which will leave us with 90 plus VF car equals VF truck. So in place of VF truck, we're going to write 90 plus VF car. So take that, bring it all the way over here, We got the left side sorted already, so now we're going to plug that in for VF truck on the right side. 400 times VF car plus 2,000. And now for the substitution, instead of VF truck, 90 plus VF car. The second unknown is eliminated, and now it's just a bit of algebra and a bit of distributive property to get where we want. Whereas if we use the kinetic energy formula, we'd have to deal with a squared and a square root. So this is just my preferred tactic. Questions arriving at this point? Okay. Next steps would be to distribute the 2,000 into this parentheses so we can try to get the VF cars consolidated. So 400 VF car plus 2,000 times 90 is 180,000. And then 2,000 times VF car is just 2,000 VF car. Is that legible? Fair enough. Doing it again. Plus 2,000 VF car. Better? All right. For lack of board space, I'm going to continue just to the left. We want the VF cars on one side and all the not VF cars on the other. So I'm going to take that 180,000 and subtract it over to the left, giving us very big negative numbers. Negative 72,000 minus 180,000. And that's going to equal 400 VF car plus 2,000 VF car. So I'll just simplify that to 24,000 VF car. Both numbers on the left will add together, but negatively. And I believe that turns into negative 252,000. We would then divide both sides by 24,000 to get VF car. And final answer, VF car should be, because let me know if your calculator disagrees, negative 105 meters per second. Negative meaning the left. Questions or issues arriving at that number? Now that we have that number, is that good news or bad news for the sports car? So at least one grimace. Yes, so the fact that it's negative in comparison to the car's initial positive velocity means that this car is going to undergo enough force to stop and then get thrown backwards very quickly. So the negative means it's turned around and its final negative speed is very fast, way faster backwards than it was going forwards. What would the car's change in velocity be given that final velocity? changing anything is always final minus initial. Final is negative 105 minus initial positive 45. So that is a delta V for the car of negative 150. Again, this is enough to take that initial 45, stop it, and then still give it 105 backwards. This delta V is huge, especially if it takes place over like a millisecond. I was very careful to disclaimer make there no driver in this car, because if a human driver underwent that change in velocity in a very short amount of time, they might be turned into paste and ejected from the windshield. Both, definitely both. Now, all that considered, the truck fares less badly. We can determine the truck's final speed as well now that we have the car's final speed. We just want to take that negative 105 and bring it back over here into our other equation. So that would be 90 plus negative 105, which is negative 15. So the truck's final velocity is negative 15, still to the left. So whereas the car gets thrown backwards, the truck is still moving in the same direction, just at 1/3 the pace. So not as bad, but still not great. Like, you wouldn't want to be in the truck when you're slowing down that fast. Slowing down that much in that amount of time. Again, just for scale, the change in velocity of the truck, final minus initial, would be negative 15 minus negative 45, which is actually positive 30. The truck's delta V points to the right, even though the truck's initial and final velocities still point to the left. This just means that its acceleration points right. It's sped up in this direction, even though it's still moving leftwards. So once again, to summarize, car loses, big time. Does this demonstrate the absurdity of elastic collisions and why we don't want cars to collide this way? Because not only would the drivers already suffer turbo whiplash, the sports car would get launched away, possibly into traffic and possibly into buildings. So just even more bad news. Because 105 meters per second is like between 1/3 to 1/4 the speed of sound. It's too dang fast. Now again, realistically, this would never happen. This is assuming a perfectly elastic collision, and those also are very rare. As much as we assume kinetic energy can be conserved in elastic collisions, it's very rarely totally conserved. Usually you still lose some of it, because if you can hear the collision, that's automatically some energy lost to sound and heat. So it's never 100% conserved. You definitely know this if you had lab this week already. And again, cars are not designed to collide this way. What would realistically happen is they'd have an inelastic crash. The car would still be turned into a pancake on the truck's grill, but they'd stick together and just roll in this direction together, not as fast as the car would get thrown backwards in an elastic collision. And that would be much lower changes in velocity for everyone involved, and therefore technically safer, even if the car still loses out very badly. Just not as bad. Truck might not notice. Bless you. Questions, comments, concerns? Feel okay with the differences between the collision types? At least the concepts involved?
So what are like perfect elastic collisions?
A perfect elastic collision would mean that 100% of the initial kinetic energy is conserved and equals the final amount. In reality, you never really get totally 100 to 100, because there's always friction, you lose energy to sound as well. So even the most elastic collisions, like the really bouncy balls, still lose some energy, and that's why they never bounce up totally to their initial height, even if it's as rubberized as it can get. But for simplicity's sake, any question, any collision question that I give you in this class, either on the homework or on a test, will tell you if the collision is elastic or inelastic. And if it's elastic, we'll just assume perfectly elastic so that this equation and this equation work. And it would kind of tell you the best or worst case scenario. Does that answer the question? Okay. Yeah, so, weird. Any homework question or any test question will tell you flat out inelastic or perfectly elastic. And based on that distinction, you should know, high speed or low speed, stick together or bounce away from each other, and it will also tell you directly which of these starting points you can use. Because if it's inelastic, you only have one choice, and that's conservation of momentum. If it's elastic, you can pick any of the three. And in fact, you might have to pick multiple of them if you end up in a 2 equations, 2 unknowns scenario. So, inelastic, slower, boring, safer, objects stick together. Elastic, ricochet, exciting, high speed, high energy, potentially more math. And I will always again tell you, if a collision is one or the other, you don't have to guess, you don't have to assume. How do you guys feel? Alright. That is technically it for chapter 6. And so what I would recommend you guys do over the weekend and over next week is work on the chapter 6 homework, because there's lots of different types of collisions in there. We've covered all of the information you would need to do them, but sometimes the question is kind of described differently. Like I did mention that cannon question we did is similar to the question where the astronaut throws something away from themselves and they both drift away. That is technically an explosion. Same is true of the question that involves sliding across ice. So the mathematical similarities are there, even if the context or flavor text is different. I recommend you guys work over those over the weekend. Note again what type of collision each question talks about, what information it gives you about initial and final speed, and let me know what unique issues you run into for each one, because I want to make sure that what am I trying to say? There's lots of different ways that collisions can be phrased, so I want you to see the different types and see how they compare back to the methods we've already used. And on Monday, by Monday, email me questions. We can also talk about homework examples in class. But that's chapter 6. And so what I want to do now is introduce the starting concepts of chapter 7. Chapter 7 is about rotation, and next week's lab is going to involve rotation. So my goal for today, it's a Friday, so I don't want to keep you long. What I want to do is introduce the very beginning concepts so that we can kind of jump straight next week into using them and talking about what next week's lab will involve next Monday. So we're going to begin chapter 7, namely getting the intro preamble out of the way, because it kind of involves a shift in thinking. That sounds vague. I'm going to make it make sense, I promise. That's why I want to start talking about it now. But any objections to introducing chapter 7 before the weekend? All right. Now, chapter 7 is about rotation. And technically chapter 8 is too. So we're actually starting an entire season of just rotating stuff. Because there's surprisingly a lot to talk about. It's an interesting concept. Up until now, everything we've talked about has been linear in nature. The term linear meaning of or referring to straight lines. It's literally linear. Everything up to now has been in straight lines. Displacement, velocity, and acceleration in straight lines, because even two-dimensional is still straight lines. It's just in more than one axis at once. Forces all point in straight lines. All these momentum vectors have been forwards or backwards in a straight line. But that's not the only way that objects can move, right? There are other movement types, namely, as it relates to this class, behold, the disembodied bike wheel of science. Is this object moving? It's not a trick. Is it moving? Yeah, you can see it in motion. The question though is it moving linearly? Is it moving in a straight line in a direction? No, this is rotating. So it is moving, but not linearly, meaning we need different terms to describe this motion in comparison to this motion. Now, those two types of motion are related. They can exist separately. You can move forwards without rotating, and you can rotate without moving forwards. But you can do them at the same time, in the case of one of man's earliest inventions. So, the two different types of motion do coexist and are very similar. There's a lot of conceptual overlap. And the thing I want to do today is introduce the beginning concepts and descriptions for rotational motion so that we can be using them next week. So today we are beginning to describe rotational motion. Now, quick disclaimer before I begin doing that, before I begin describing rotational motion. I'm out of board and I don't want to erase anything. The word angular is going to pop up. In fact, I'm actually going to retype it on this slide. Angular is a synonym for rotational. And I'm bringing this up now because I use the words interchangeably. If two things are interchangeable in my brain, which one comes out is just a coin flip. So when I say the word angular, that means rotational. It is in contrast to linear, linear, of or referring to straight lines, because rotational motion instead talks about angles, angle r of or referring to angles. Because if I take this wheel and spin it again, linear motion, if I ask you how much does something move linearly, you can measure, meters in a straight line. Angularly though, rotationally, no. If I ask you how much is this thing moving, you can't tell me a number of meters it's moving because I'm technically holding it still. Instead, if I ask you how much does this thing move, what kind of information would you think to give me?
Like degrees or something?
Perfect. How many degrees it rotates through? Does that sound like an okay way to describe magnitude of rotation? Ow. So rotational motion uses angles to describe magnitude of movement, whereas linear motion uses meters. And that's why it's called angular motion. It's angle rotation rather than straight lines. So that's where the word comes from. And I'm going to use angular and rotational as synonyms. Want to acknowledge that now. Does that feel okay? Okay. So, kind of, nope, that's the wrong menu. There we go. Kind of jumping off from what I just said, if I was to ask you to describe the magnitude of rotational displacement, you would think to tell me like how far something rotates, how many angles something rotates through. I'm going to be picking this wheel up a lot this week. So, if I do this, note where this piece of metal and my hand starts. If I do this, how would you describe that motion? Sorry? It would actually be pi radians. But how would you describe it in degrees?
180.
180 degrees, very good. So, the number of angles that something rotates through is angular displacement, rotational displacement. So, the way that I think about the difference between linear and angular, the linear rotational stuff, is they actually work weirdly similarly. Pretty much all of the terms and all the logic we've built up for all the linear stuff we've been doing so far still applies to the rotational stuff because, we can describe linear displacement, meters in a straight line, and likewise we can describe rotational displacement as, the amount of angles that something is going to move through. The more times it rotates, the bigger the displacement. The main difference that exists between linear and angular is just framing it as spinning and the magnitude of the spin rather than the magnitude of the line. So angularly, instead of delta x measured in meters, we describe angular displacement as delta theta in radians. Degrees technically works, but unfortunately most physics formulas are designed to use radians, that other unit for angle measurement. Radians and degrees are basically the same to each other as feet are to meters. You can convert them back and forth. And you're not going to have to take your calculator out of degrees mode, because technically none of the radians we use for this rotational stuff are going to have to be put into a trig function. As much as you guys loathe the trig, we're actually in a part of the course that doesn't use it as much. It'll still be on the final, but we're not going to need any for the next 2 weeks. So, no trig. This theta isn't the trig theta, it's the theta of how many degrees does something rotate through. So, technically it's used the same in the pictures, but you're not going to have to put it into a trig function for right now. So, when these are in radians, that does not mean you have to translate your calculator. You don't have to turn your calculator to mode. And we'll talk about converting, degrees into radians as it comes up. But as a general rule, if you want to write this in your notes, 360 degrees is equal to a number of radians of 2 times pi. That's the basic conversion that we'll be using once it comes up. So, magnitude of displacement is meters in a straight line and radians if you are rotating. So we're just comparing straight line motion to amount of spin. That's the baseline difference between linear motion and angular motion. That's the main difference to wrap your head around. And once that assumption is made, all the other linear concepts still apply to rotating. We're just using radians instead of meters. For example, if I was to spin this, could you tell me how fast it was spinning? How many radians or degrees it rotates through every second? Is that a thing that could be done hypothetically? And it turns out that your car does this for you. That's what the RPM meter is. That is rotations per minute. Not necessarily of the tires, but of some parts of it, depending on the build. Is it the tires? I don't do cars much. Point is, the term rotations per minute is an angular velocity or angular speed. The word speed might be used a bit more because angular vectors really only point forwards or backwards. You don't really have to specify like axis. It's just, you know, is it spinning clockwise or counterclockwise? So angular velocity, angular speed is literally just how fast is it spinning per second? How many degrees or how many radians does it pass through every second, rather than how many meters forward does it move every second? And for that reason, the formulas are basically identical. Linear velocity is displacement over time. Angular velocity is displacement over time. It's just the angular displacement, the rotational displacement, instead of the linear displacement. Same basic formula, but it's how fast are you spinning instead of how fast are you moving forwards. And all the same logic and quirks still apply. Now, angular velocity does have its own variable, just to distinguish it in the formulas. Instead of English v, the letter it uses is a lowercase Greek omega. This weird W looking thing is technically an omega. It's just a lowercase one. You are allowed to call it W, you are allowed to call it mustache. Because when I looked at that, depending on who's writing it, it does kind of look like villain mustache. A little bit anyway. But when I read this out loud, I'm likely to say omega equals theta over t. And it is just technically the velocity formula again. So really at this point, we're just kind of going through those first three variables again, just replacing meters with radians, if I'm being honest. So this is measured in radians per second. It's, or optionally degrees per second or rotations per second. It's just how much spin happens every unit time. Feel all right so far? All right. Now, after velocity, what was the next concept we discussed linearly in regards to motion? Sorry? That was the first one. We went from displacement to velocity to acceleration. Because linearly, your velocity can change. You can speed up. And rotationally, you can also change speed. If this was attached to a bicycle, you could start at rest and then start pedaling and speed up over time. So the amount of rotation can change with time, and that's where angular acceleration comes from. Linear acceleration is change in velocity over time. Angular acceleration is change in angular velocity over time. Again, all the same logic applies. The only difference is we're using Greek instead of English, Gesundheit. And we're using radians instead of meters. Now, all the angular variables do have their own symbols just to keep them distinct. And the symbol, I wouldn't fault you for not noticing a difference here. Acceleration is A. Angular acceleration is technically lowercase alpha. And there is a small difference. Granted, a computer isn't very good at noting the difference. A has a very tiny vertical stem on it. Alpha has a tail, an upward tail that kind of tilts outward instead of up. It's kind of annoying to notice if a computer's doing it. When I'm doing it by hand, I tend to just give A no upper tail, and I tend to overemphasize alpha's upper tail and make it a fish. I feel as though the Jesus fish may actually be the letter alpha. I'm not a historian, so I'm not super qualified to say that, but I'm pretty sure there's a connection. So So if I read this out loud, I would probably say alpha equals omega over t, but you are allowed to say fish equals w over t. If calling them fish and w, keep them straight in your brains. I have plenty of students who say fish. Good okay so far, I hope? All right, so like how displacement, velocity, acceleration are our first linear vectors, the same is true angularly as well. I just noticed how out of ink my marker is. That's not better. Fish. There we go. So when I'm writing it by hand, I'll make it very clear if it's A or alpha. And all these new concepts refer directly back to their old linear counterparts, to the point where the formulas for the angular terms are the exact same as the linear ones, just using Greek instead of English. Literally, direct corollary. We've already looked at the velocity and acceleration equations, but even equation 3 and 4 from the beginning of the course have angular counterparts. If you're accelerating over time, you are displacing while that happens, and as you displace while accelerating, your velocity changes. Same formulas, just Greek instead of English, or I guess Latin letters, and also radians in place of meters. So we've got radians, radians per second squared. And because of the direct correlation between the formulas, your formula sheet has listed the linear and angular boxes as opposite each other the entire time. The first 4 formulas have always been labeled linear. I've just never acknowledged that until now. And directly opposite them, arranged the same way, are the angular ones labeled angular. So my goal is that the sheet enforces the similarities again. There is a weird box in the middle, and those formulas are designed to convert one into the other, because if a wheel is rolling forwards, its angular displacement is tied to its linear displacement, and you can convert one into the other using this middle box here. But that's what we're going to do next week. Right now, main goal is just introduce the concepts, because it's what we're going to be using all next week. How do you guys feel? Any objections at least? All right. That's pretty much everything I wanted to get through today. So main takeaways are, next 2 weeks at least is going to be spinning stuff. Lab next week, starting. Next couple of labs are actually going to all involve rotation. So again, I want to show you these so we can learn more about it on Monday, and then that information from Monday should cover the lab for next week. I think the next 3 or so labs I'm planning all involve spinning. You should also work on Chapter 6 homework and look at the different types of collision questions there and let me know any issues you encounter. And have a great weekend. Stay dry. Is it still raining? I don't know.